Tonight, we're going to talk about something you use every single day without thinking about it. Something so ordinary, so seamlessly woven into your life that you'd only notice it if it suddenly stopped working. Right now, at this very moment, there's a small blue dot on your phone screen. Maybe you used it today to find a coffee shop you'd never been to before. Maybe you used it to navigate through unfamiliar streets in a city you were visiting. Maybe you just glanced at it to see how far you were from home. That little blue dot seems simple. It seems obvious. It's just there, hovering over a digital map, following you as you move through the world. But that dot represents one of the most extraordinary achievements in human history. It exists because of invisible conversations happening between your phone and machines, floating 12,000 miles above your head in the vacuum of space. Before we dive into this story, if this kind of exploration interests you, if you find yourself drawn to understanding the hidden mechanics of the cosmos, a like or subscribe would mean the world to me. It's a small gesture, just a single tap, but it helps this channel grow. It helps me continue making these deep explorations into the nature of reality. So, if you're the kind of person who wants to know the real story behind the tools you use every day, please take a moment to like this video and subscribe to Space Doze. Now, let's begin. That blue dot exists because we've learned to measure time with such impossible precision that we can detect differences of 1/1000th of a second. And most remarkably, it exists because a 26-year-old patent clerk working in Switzerland in 1905 figured out that space and time are not what they seem, that they bend, that they warp, that reality itself is flexible in ways that completely violate our everyday experience. Without his insights, without the mathematics he worked out, that blue dot on your screen wouldn't work. It would drift. It would lie to you. Within hours, it would tell you that you're in a completely different city from where you actually are. Your GPS would be useless. Not because of any engineering failure, not because satellites broke down or signals got scrambled, but because the universe itself operates according to rules that seem impossible until you actually measure them. Think about what that means for a moment. You're standing on solid ground right now, or sitting in a chair feeling perfectly still and stable. The world around you seems fixed, unchanging, reliable. But that's an illusion. You're actually standing on a planet that's spinning at roughly 1,000 miles per hour at the equator. That planet is orbiting the Sun at about 67,000 miles per hour. The Sun itself is racing around the center of the Milky Way galaxy at approximately 514,000 miles per hour. And the entire galaxy is hurtling through space at speeds that make all of these other motions look slow. You are moving through space at velocities so extreme that if you could somehow see them, if you could somehow feel them, they would terrify you. But you don't feel any of it, because everything around you is moving together. The air you breathe, the ground beneath your feet, the buildings and trees and other people, all of it is carried along on this cosmic carousel. And because of that, because we're all moving together, our everyday experience tells us that we're standing still. Our intuition tells us that space is space, and time is time, that an hour is an hour everywhere in the universe, that distances are fixed and absolute. Our intuition is wrong. Spectacularly, completely, measurably wrong. Let's talk about what's really happening when you look at that blue dot on your phone. The system is called GPS, which stands for Global Positioning System, though these days people use the term generically to mean any satellite navigation system, including Russia's GLONASS, Europe's Galileo, and China's Beidou. But they all work on the same fundamental principle, and they all face the same fundamental challenge. They all have to deal with the fact that reality bends. Here's what's actually happening. Right now, scattered across the sky above you, there are more than 30 satellites in the GPS constellation alone. Each one weighs about 2,000 pounds and is roughly the size of a car with its solar panels extended. They orbit at an altitude of approximately 12,550 miles, which is about 20,200 kilometers. They're moving at speeds of around 8,700 miles per hour, or about 14,000 kilometers per hour. And each one carries something precious, something that took decades of quantum physics and precision engineering to perfect. Each satellite carries atomic clocks. Multiple atomic clocks, actually, as redundancy and backup. These aren't clocks in the sense you normally think of them. They're not measuring time by counting the swing of a pendulum or the vibration of a quartz crystal or the rotation of gears. They're measuring time by counting the oscillations of atoms, specifically cesium-133 atoms, which vibrate at an extraordinarily precise frequency when stimulated with microwave radiation. The frequency is exactly 9,192,631,770 cycles per second. Not approximately, not roughly, exactly. This number is so precise, so reliable, so unchanging that in 1967, the international scientific community redefined the second itself based on these atomic oscillations. 1 second is now officially defined as exactly 9,631,1170 periods of the radiation, corresponding to the transition between two specific energy levels of the cesium-133 atom. The second is no longer based on the Earth's rotation or the planet's orbit around the Sun. It's based on the vibration of atoms. These atomic clocks are astonishingly accurate. The best ones lose or gain only about 1 second every 100 million years. Think about that. If you had started one of these clocks at the moment the dinosaurs went extinct 66 million years ago and let it run continuously until today, it would be off by less than a second. That level of precision seems absurd, seems like ridiculous overkill for any practical purpose. But for GPS, for the system that puts that blue dot on your screen, this precision is barely adequate. In fact, if these clocks were only 1,000 times less accurate, GPS wouldn't work at all. You'd look at your phone's map and see yourself drifting across the landscape like a ghost, your location jumping randomly from block to block, from neighborhood to neighborhood, completely useless for navigation. The reason comes down to one fundamental fact about the universe. Light, and by extension, all electromagnetic radiation, including the radio waves that GPS satellites use to communicate, travels at a finite speed. Not infinitely fast, but at exactly 299,592,458 meters per second in a vacuum, which is approximately 186 to 282 miles per second. This is the speed limit of the universe, the fastest. That information can possibly travel through space. And at this speed, light covers about 30 centimeters, roughly 1 foot, in a single nanosecond. 1/1000th of a second. That's the key to everything. GPS works by measuring time. Your phone receives signals from multiple satellites, and each signal contains a timestamp, a precise record of when it was sent. Your phone knows when it received the signal. The difference between when it was sent and when it was received tells you how long the signal took to travel. And because you know the signal traveled at the speed of light, you can calculate the distance. If the signal took 1 millisecond to arrive, that's 1,000th of a second, which means it traveled about 186 miles. The math is simple. Distance equals speed multiplied by time. But here's the problem. If your time measurement is off by even 1 microsecond, 1 millionth of a second, your distance calculation is wrong by about 300 meters, roughly 1,000 feet. If it's off by 1 nanosecond, you're wrong by about 1 foot. So to get your position accurate to within a few meters, which is what modern GPS achieves, you need clocks that stay synchronized to within a few nanoseconds. Not a few seconds, not a few milliseconds, a few billionths of a second. And that's where Einstein comes in. Because it turns out when you put atomic clocks in satellites and send them racing around the Earth at 8,700 miles per hour, 12,550 miles above the ground, something very strange happens. The clocks don't tick at the same rate as identical clocks on the ground. They run faster, significantly faster, measurably faster, about 38 microseconds per day faster, which doesn't sound like much until you realize that 38 microseconds at the speed of light equals about 11 kilometers, or roughly 7 miles. Without correcting for this effect, your GPS position would drift by 7 miles every single day. Within a week, the system would be telling you you're in a different city. Within a month, a different state. The system would be completely, utterly useless. And the only reason we know how to correct for this, the only reason GPS works at all, is because Albert Einstein, working with nothing but a pencil, paper, and his extraordinary imagination, figured out that time itself is not constant. That it bends and stretches depending on how fast you're moving and how deep you are in a gravitational field. That the universe operates according to rules so strange, so counterintuitive, so completely divorced from everyday experience that even he initially had trouble believing them. To understand why Einstein's equations matter for something as mundane as finding your way to a restaurant, we need to understand how GPS actually works. And the first thing you need to know is that GPS is not really a map. It's a constellation of clocks, a network of extraordinarily precise timepieces orbiting Earth in a carefully choreographed dance that's been running continuously since the first satellite launched in 1978. Right now, at this very moment, there are 31 operational GPS satellites circling the planet. The official constellation requires a minimum of 24 satellites to provide global coverage, but the system maintains extras for redundancy and improved accuracy. These satellites are not clustered together. They're spread across 6 different orbital planes, each plane tilted at 55 degrees relative to Earth's equator. This arrangement ensures that no matter where you are on the planet's surface, at least 4 satellites are visible above your horizon at any given time. And that number, 4, is not arbitrary. It's the minimum number needed to determine your position in 3-dimensional space. Think of it this way. Imagine you're trying to figure out where you're standing using only distance measurements to known landmarks. If someone tells you that you're exactly 100 miles from New York City, that gives you some information, but not much. You could be anywhere on a sphere with a 100-mile radius centered on New York. You're somewhere on that sphere, but that's still an infinite number of possible locations. Now, if someone adds that you're also exactly 80 miles from Philadelphia, that narrows things down considerably. You're now somewhere on the circle where those 2 spheres intersect. Still infinite points, but you've gone from a 2-dimensional surface to a 1-dimensional line. Add a third distance, say 90 miles from Boston, and those 3 spheres intersect at just 2 points. One of those points will typically be somewhere absurd, like deep underground or floating in space, so you can eliminate it. That leaves one location. You've found yourself. That's called trilateration, and it's the geometric principle that makes GPS work. But there's a complication. To calculate distance from a satellite, you need to know exactly when the satellite sent its signal and exactly when you received it. The difference tells you the travel time, and travel time multiplied by the speed of light gives you distance. But here's the problem. Your phone doesn't have an atomic clock. Atomic clocks are expensive, delicate, power-hungry devices that require careful shielding and temperature control. You can't put one in a smartphone. So your phone's clock, relatively speaking, is garbage. It's accurate enough for daily life, but it's nowhere near precise enough for GPS calculations. Even a cheap quartz watch gains or loses several seconds per month. For GPS, where a nanosecond of error equals a foot of position error, that kind of imprecision would be catastrophic. The solution is elegant. You use a fourth satellite. With signals from 4 satellites instead of 3, your phone can solve for 4 unknowns instead of 3. It can calculate your X position, your Y position, your Z position, and the error in your phone's clock, all at once. The 4th satellite signal provides the extra information needed to determine how far off your phone's clock is and correct for it mathematically. This is why GPS requires a lock on 4 satellites minimum. 3 would be enough if your phone had a perfect clock, but it doesn't, so you need 4. Now, let's talk about what these satellites are actually doing up there. Each GPS satellite follows a nearly circular orbit at an altitude of 12,550 miles, or 20,200 kilometers. At this altitude, they complete one full orbit every 11 hours and 58 minutes. That's just under 12 hours, which means a satellite passes over the same spot on Earth twice a day, but about 4 minutes earlier each day. The orbits are designed to be highly stable and predictable. Ground stations track each satellite continuously, measuring its position with extraordinary precision using lasers and radio signals. This tracking data is uploaded to the satellites regularly, and the satellites include it in the signals they broadcast. So when your phone receives a signal from a satellite, that signal contains not just a timestamp, but also the satellite's exact position at the moment it sent the signal. Your phone knows where the satellite was and when it sent the message. From that information, it can calculate how far away the satellite was. The satellites broadcast on 2 main frequencies for civilian use, designated L1 and L2, at 1575.42 MHz and 1227.60 MHz, respectively. These are microwave frequencies, the same general part of the electromagnetic spectrum used by cell phones and Wi-Fi routers, though at different specific frequencies. The signals are relatively weak by the time they reach the ground. Each satellite transmits with only about 50 watts of power, roughly the same as a household light bulb. By the time that signal travels 12,550 miles through space, it's incredibly faint. Your phone is essentially listening for a whisper from orbit. This is why GPS doesn't work well indoors or in dense urban canyons surrounded by tall buildings. The signals are so weak that even ordinary walls or the metal roofs of cars can block them. You need a relatively clear view of the sky to pick up enough satellites for a position fix. The satellites don't just send a timestamp. They send a complex coded signal that your phone has to decode. The signal contains several pieces of information. First, there's a precise timestamp from the satellite's atomic clock, accurate to within a few nanoseconds. Second, there's ephemeris data, which describes the satellite's exact orbital position. Third, there's almanac data, which gives approximate information about all the other satellites in the constellation, helping your phone figure out which satellites are visible and where to look for them. All of this information is encoded in the signal using a technique called spread spectrum modulation. The actual data rate is quite slow, only 50 bits per second. It takes 12.5 minutes to download the complete almanac data for all satellites. This is why GPS can be slow to acquire a position when you first turn it on, a phenomenon called a cold start. Your phone needs to download enough data from the satellites to figure out where it is. Once it has that initial lock, it can update much faster because it already knows approximately where it is and which satellites should be visible. Here's something that trips people up. Your phone doesn't send any signals to the satellites. GPS is purely passive from the user's perspective. The satellites broadcast continuously, and your phone just listens. This is why GPS works for an unlimited number of users simultaneously without any interference or coordination. Whether one person or a billion people are using GPS in a given area makes no difference to the satellites. They're simply broadcasting their position and time to anyone listening. This also means GPS itself doesn't track you. The satellites don't know you exist. Your phone calculates its own position locally using the signals it receives. Now, your phone might then send that position to other services, like a mapping app or a social media platform, but that's a separate process. The GPS system itself is anonymous. The precision required for this system to work is almost impossible to comprehend. Remember, light travels 1 foot in a nanosecond. To determine your position to within 10 feet, you need timing accurate to within 10 nanoseconds. To get meter-level accuracy, you need nanosecond-level timing. And the satellites are moving at 700 miles per hour, covering more than 2 miles every second. In the time it takes their signal to reach the ground, which is about 0.067 seconds, each satellite has moved roughly 150 yards. All of this motion and timing has to be accounted for precisely. The satellites know their own positions to within about 1 meter at any given moment. Ground control stations track them continuously, making tiny adjustments to their broadcast ephemeris data to keep the position information accurate. These control stations are scattered around the world, and they monitor every satellite in the constellation 24 hours a day, 365 days a year. It's a massive, complex operation that runs continuously in the background, invisible to users, keeping that blue dot on your screen accurate. And here's where things get really interesting. When engineers first designed GPS in the 1970s, they had to account for something that seemed absurd. They had to account for the fact that time itself runs at different rates, depending on where you are and how fast you're moving. The atomic clocks on the satellites would not tick at the same rate as atomic clocks on the ground, not because of any imperfection in the clocks, but because of the fundamental nature of space-time itself. Reality warps near massive objects like Earth, and reality warps for objects in motion. These effects are tiny, but they're real, and they're large enough to completely destroy GPS accuracy if you don't correct for them. To understand why this happens, we need to go back in time. Back to 1676, to a Danish astronomer staring at Jupiter's moons, about to make a discovery that would eventually lead to Einstein's revolution, and, ultimately, to the GPS satellites orbiting above us right now. Before we can understand why Einstein's equations matter for GPS, we need to understand what makes these satellite clocks so special. We need to understand why they're accurate to 1 second in 100 million years, and why that level of precision is barely good enough. The atomic clock is one of humanity's most remarkable inventions, a device that measures time not by mechanical motion or electronic oscillation, but by counting the vibrations of nature itself at its most fundamental level. To understand how it works, we need to zoom in, way in, down past the level of everyday objects, past molecules, past the scale where chemistry happens, down to individual atoms. An atom is mostly empty space. If you could somehow expand an atom to the size of a football stadium, the nucleus would be smaller than a marble sitting at the center of the field, and the electrons would be tiny specks orbiting somewhere up in the highest seats. Between them, nothing but void. And yet, despite this emptiness, atoms have structure, they have architecture. The electrons don't orbit randomly. They occupy specific energy levels like runners on different lanes of a track. And the distances between these energy levels are not arbitrary. They're determined by the fundamental laws of quantum mechanics. Here's what matters for our story. When an electron jumps from one energy level to another, It either absorbs or emits a photon, a particle of light. The photon's energy is exactly equal to the difference between the two energy levels. And because energy and frequency are related, this means each possible electron transition corresponds to a specific, exact frequency of light. For any given type of atom, these frequencies are always the same. A cesium-133 atom in Tokyo has exactly the same energy levels as a cesium-133 atom in New York or London or anywhere else in the universe. The laws of quantum mechanics don't change from place to place. This makes atoms perfect clocks. They vibrate at frequencies that are determined by the fundamental constants of nature, frequencies that never drift or change or wear out. The specific transition used in cesium atomic clocks involves two hyperfine energy levels of the ground state of the cesium-133 atom. The frequency is exactly 9,192, 631, 170 cycles per second. This number is now the definition of the second. In 1967, the International Committee for Weights and Measures officially redefined the second based on this atomic transition. 1 second is no longer based on Earth's rotation or the planet's orbit. It's exactly 9,292 to 631,170 periods of this cesium transition. The second is now based on atomic physics, on quantum mechanics, on the fundamental structure of reality at its smallest scales. Here's how a cesium atomic clock actually works. You start with a beam of cesium atoms, heated in an oven until they vaporize and stream out into a vacuum chamber. These atoms are in various energy states. You pass this beam through a magnetic field that separates the atoms based on their energy state. You keep only the atoms in the lower energy state and send them forward. Now, you hit these atoms with microwave radiation. If the frequency of this radiation is exactly right, exactly 9,102 to 631,570 Hertz, the atoms absorb the energy and jump to the higher energy state. If the frequency is even slightly wrong, they don't absorb much and remain in the lower state. At the end of the chamber, another magnetic field separates them by energy state again. You count how many atoms made it to the higher state. If that number is high, your microwave frequency was correct. If it's low, your frequency was off. You use this feedback to tune your microwave generator, constantly adjusting it to maximize the number of atoms that make the transition. The result is a microwave signal locked to the atomic transition frequency with extraordinary precision. The best cesium atomic clocks can now maintain accuracy to within 1 second over 100 million years. That's an uncertainty of about 1 part in 10 to the 15th power, 1 quadrillionth. To put that in perspective, if you had a ruler 1 quadrillionth off in its measurements, and you used it to measure the distance from Earth to the Sun, about 93 million miles, your measurement would be off by less than the width of a human hair. Scientists have developed even more accurate clocks using optical transitions instead of microwave transitions. These optical atomic clocks, using atoms like strontium or ytterbium, can be accurate to 1 second in 15 billion years. That's longer than the current age of the universe. These clocks are so precise they can detect the gravitational time dilation caused by raising them just 1 centimeter. Lift the clock 1 centimeter higher and it ticks measurably faster because gravity is slightly weaker at that height. For GPS satellites, each one carries multiple atomic clocks as backup. The current Block 3 satellites carry both rubidium and cesium atomic clocks. The rubidium clocks are more stable over short periods, while cesium clocks are more stable over longer periods. By comparing multiple clocks, the system achieves even better timekeeping than any single clock could provide. And they need this precision. Remember, GPS works by measuring the time it takes for signals to travel from satellites to your phone. Light travels 1 foot in 1 nanosecond. If the satellite's clock is off by just 10 nanoseconds, your position calculation is wrong by 10 feet. If it's off by a microsecond, you're wrong by about 1,000 feet. To achieve the few-meter accuracy that modern GPS provides, the clocks need to be synchronized to within a few nanoseconds. This is where the story gets interesting. When you take an atomic clock and put it in a satellite, something strange happens. The clock doesn't run at the same rate as an identical clock on the ground, not because anything is wrong with the clock, but because time itself behaves differently up there. Two effects are at play, and they work in opposite directions. First, the satellite is moving fast, about 8,700 miles per hour. According to special relativity, Einstein's 1905 theory, moving clocks run slow. From the perspective of someone on the ground, the satellite's clock should tick slower than ground clocks because of its high velocity. At 8,700 miles per hour, a clock loses about 7 microseconds per day compared to a stationary clock. Second, the satellite is high up, about 12 to 150 miles above Earth's surface. According to general relativity, Einstein's 1915 theory, clocks in weaker gravitational fields run fast. The satellite is farther from Earth's center of mass, so it experiences weaker gravity than we do on the surface. This causes its clock to gain about 45 microseconds per day compared to ground clocks. These two effects work against each other. The velocity effect makes the satellite clock run slow by 7 microseconds per day. The gravitational effect makes it run fast by 45 microseconds per day. The net result is that the satellite clock runs fast by about 38 microseconds per day. That's the difference that matters. 38 microseconds, which sounds tiny until you convert it to distance. Light travels about 300 meters, roughly 1,000 feet in 1 microsecond. So 38 microseconds equals about 11,400 meters, or roughly 7 miles. If GPS didn't correct for this effect, your position would drift by 7 miles every single day. After a week, the error would be 49 miles. After a month, over 200 miles. The system would be completely useless. And this isn't a hypothetical problem, it's real. When GPS was first being developed in the 1970s, there was actually debate about whether these relativistic effects would matter. Some engineers thought they could be ignored or corrected for later if they turned out to be significant. But physicists insisted that the effects were large enough to destroy the system's accuracy if not accounted for from the beginning. They were right. The solution is remarkable in its simplicity. Before a satellite is launched, its atomic clocks are set to run at a slightly different frequency than ground clocks. Instead of ticking at exactly 10.23 megahertz, they're set to 10.99999999943 megahertz. That's a difference of about 4.57 parts in 10 to the 10th power. Once the satellite reaches orbit and experiences the combined effects of its velocity and the weaker gravity, this pre-adjusted frequency causes the clock to tick at exactly 10 to 123 megahertz as measured by observers on the ground. The relativistic effects are cancelled out by engineering, by deliberately building clocks that would be wrong on Earth but are right in orbit. This is Einstein's equations being used not just to predict something, but to design and build a functional technology that billions of people use every day. To understand why Einstein's theories matter for GPS, we need to understand something fundamental about the universe. There's a speed limit, a cosmic speed limit built into the fabric of reality itself. Nothing can travel faster than light. Not spaceships, not information, not cause and effect. This isn't a technological limitation that we might overcome with better engineering. It's a fundamental feature of how space-time works. And discovering this speed limit, measuring it, understanding what it means took humanity nearly 400 years of careful observation and brilliant insight. The story begins in 1676 with a Danish astronomer named Ole Rømer, who was studying something that seemed completely unrelated to the speed of light. He was watching the moons of Jupiter. Jupiter has 4 large moons, discovered by Galileo in 1610 when he first pointed a telescope at the night sky. These moons orbit Jupiter just as our moon orbits Earth, and they do so with clockwork regularity. Io, the innermost of the 4 large moons, completes one orbit every 42.5 hours. As it circles Jupiter, it periodically passes behind the planet from our perspective, disappearing from view. These events are called occultations, and astronomers in the 1600s used them for navigation. If you could predict exactly when Io would disappear behind Jupiter, you could use those predictions to determine your longitude at sea. Ships would carry astronomical tables, and by comparing predicted times to actual observations, sailors could calculate how far east or west they were. It was an early form of celestial GPS. Rømer was working at the Paris Observatory under Giovanni Cassini. His job was to create precise tables of Io's occultations. And as he compiled observations over months and years, he noticed something strange. The occultations didn't happen exactly when predicted. When Earth was moving toward Jupiter in its orbit, the occultations happened slightly early. When Earth was moving away from Jupiter, they happened late. The discrepancy accumulated over time. By the time Earth had moved from one side of its orbit to the other, about 6 months, the timing errors added up to about 22 minutes. Io's occultations were 22 minutes late when Earth was farthest from Jupiter compared to when Earth was closest. Most astronomers assumed this was observational error, or perhaps some irregularity in Io's orbit. But Rømer realized there was a simpler explanation. Light takes time to travel. When Earth is closer to Jupiter, the light has less distance to cover, so we see the events sooner. When Earth is farther away, light has to travel an extra distance equal to the diameter of Earth's orbit, and that takes extra time. The 22-minute difference represents the time light needs to cross the diameter of Earth's orbit. This was revolutionary. For thousands of years, people had assumed light traveled instantaneously. Aristotle had declared light propagation instantaneous, and his word had carried enormous weight for centuries. Even Galileo had tried to measure light speed using lanterns on distant hilltops, but the experiment failed because human reaction time was far too slow. Rømer's insight was different. He wasn't trying to measure light speed directly. He was observing astronomical events over months and noticing a pattern that could only be explained if light had a finite speed. On September 1st, 1676, he made a bold prediction. He announced that the occultation of Io scheduled for November 9th would occur 10 minutes later than the standard tables predicted. The reason? Earth would be farther from Jupiter by then, and light would need extra time to make the journey. On November 9th, astronomers watched and waited. The occultation occurred exactly 10 minutes late, precisely as Rømer had predicted. This was the first successful measurement of light speed in human history. Rømer estimated that light takes about 22 minutes to cross the diameter of Earth's orbit. Since astronomers didn't know the exact size of Earth's orbit, his calculation was off by about 25%. He got roughly 140,000 miles per second. The actual speed is about 186,282 miles per second. But he had proven the essential point. Light has a speed. It travels incredibly fast, but it still takes time to get from place to place. It would take another 53 years for independent confirmation. In 1728, English astronomer James Bradley made a different discovery that also proved light had a finite speed. He was trying to detect stellar parallax, the slight shift in star positions caused by Earth orbiting the Sun. What he found instead was stellar aberration. Stars appeared to shift position by about 40 arcseconds over the course of a year, but in the wrong direction and wrong timing for parallax. The stars seemed to be displaced in the direction Earth was moving. The explanation came, legend says, while Bradley was sailing on the Thames River. He noticed that the wind's direction relative to his boat seemed to change when the boat changed direction, even though the actual wind hadn't shifted. He realized stars behave the same way. Picture walking through falling snow. Even if the snow is falling straight down, you have to tilt your umbrella forward because you're moving into the falling snow. Starlight does the same thing. It appears slightly displaced in the direction of Earth's orbital motion. This phenomenon only makes sense if light takes time to travel. If light arrived instantly, there would be no aberration. Bradley calculated light speed at between 183,000 and 187,000 miles per second. He was within 2% of the modern value. The next major advance came from trying to measure light speed on Earth without relying on astronomical distances. In 1849, French physicist Armand Fizeau performed an elegant experiment. He set up a light source on a bell tower in Suresnes, a suburb of Paris. About 5.4 miles away on Montmartre Hill, he placed a mirror. Between the light source and the mirror, he positioned a toothed wheel with 720 teeth. Light from the source passed between two teeth, traveled to the distant mirror, bounced back, and returned to the wheel. If the wheel wasn't spinning, the returning light would pass back through the same gap. But if the wheel was spinning at just the right speed, by the time the light returned, the wheel would have rotated enough that a tooth blocked the path. By adjusting the wheel's rotation speed, Fizeau could find the exact speed where the returning light was blocked, and then where it passed through the next gap. At 25.2 rotations per second, the returning light passed through the next gap. From this, knowing the wheel's rotation speed, the number of teeth, and the distance, he calculated light's velocity. His result was about 194,600 miles per second. This was about 4.5% too high, but it was a triumph. For the first time, light speed had been measured without relying on astronomical distances. Fizeau's work was refined by other physicists. Léon Foucault, using rotating mirrors instead of toothed wheels, measured light speed at about 185,000 miles per second in 1862, only 0.6% different from the modern value. But Foucault did something even more important in 1850. He demonstrated that light travels slower in water than in air. This might seem minor, but it was decisive evidence in one of physics' longest-running debates. Isaac Newton had proposed that light consisted of tiny particles called corpuscles. According to Newton's theory, light should travel faster in denser materials because the particles would be pulled in and accelerated. The competing wave theory predicted the opposite. Light waves should slow down in denser media. Foucault's experiment showed that light travels slower in water. The wave theory was correct. Newton had gotten this one wrong. This brings us to the 1880s, and one of the most important experiments in the history of physics. An experiment that failed to find what it was looking for, but in failing, paved the way for Einstein's revolution. The experiment was conducted by Albert Michelson and Edward Morley in 1887, and it was designed to detect something called the luminiferous ether. In the late 19th century, physicists believed that light waves, like sound waves, needed a medium to travel through. Sound requires air or water. You can't hear anything in a vacuum. So what did light waves travel through? What carried them across the emptiness of space, from the sun to Earth? Scientists proposed the existence of the ether, an invisible, weightless material that filled all of space and carried light waves the way air carries sound. If the ether existed, and if Earth moved through it as our planet orbited the Sun, then light should travel at slightly different speeds, depending on direction. Light traveling in the direction of Earth's motion would be swimming against the current and should move slightly slower. Light traveling perpendicular wouldn't face this resistance. The difference would be small, but with sensitive equipment, it should be detectable. Michelson and Morley designed an interferometer to detect this difference. The device split a beam of light into two perpendicular paths, bounced each beam off mirrors, and recombined them. If one path was faster than the other, the recombined beams would be slightly out of sync, creating an interference pattern that could be measured precisely. They set up the experiment in the basement of a dormitory at what is now Case Western Reserve University in Cleveland. The apparatus was mounted on a large sandstone slab, floating in mercury to isolate it from vibrations. The effective path length was about 36 feet through multiple mirror reflections. Based on their calculations, they expected to see a fringe shift of about 0.4 fringes as they rotated the apparatus. From April through July of 1887, Michelson and Morley conducted their measurements. The result was nothing. The measured displacement was less than 1/40th of what they expected. There was no difference in light speed regardless of which direction they pointed their apparatus. Light traveled at exactly the same speed in every direction, regardless of Earth's motion through space. This is often called the most famous failed experiment in scientific history. Michelson and Morley had set out to measure Earth's motion through the ether and instead prove that the ether didn't exist, or at least didn't affect light the way everyone assumed. For his precision optical instruments, Michelson received the Nobel Prize in 1907, becoming the first American to win the Nobel Prize in any science. The experiment had raised a deep puzzle. If there was no ether, what carried light waves? And why didn't Earth's motion affect light speed? The answer would require completely rethinking our understanding of space and time. It would require a revolution. And that revolution came in 1905 from an unlikely source. A 26-year-old patent clerk working in Switzerland who had been thinking about light and motion since he was a teenager. Albert Einstein was born in 1879 in Ulm, Germany. He wasn't a child prodigy in the traditional sense. He didn't speak until he was relatively late, and his parents worried about him. He wasn't the best student, often clashing with teachers who valued memorization over understanding. He questioned everything, pushed back against authority, and generally made himself difficult to teach in the rigid German school system of the time. But Einstein had something more valuable than obedience. He had an incredible imagination. He could visualize abstract concepts in ways that made them clear and understandable. He thought in pictures, in thought experiments, in scenarios he could play out in his mind. This ability to visualize the invisible would become his greatest strength. When Einstein was about 16 years old, sometime around 1895, he began thinking about a thought experiment that would haunt him for the next decade. He imagined himself chasing a beam of light. What would happen if you could run alongside a light wave, matching its speed? If you could somehow travel at the speed of light and look over at a light beam traveling next to you, what would you see? According to the physics of his time, you should see a frozen wave, a stationary oscillation in the electromagnetic field, just sitting there next to you as you both traveled through space. But this made no sense. James Clerk Maxwell's equations, which described electromagnetism with extraordinary accuracy, didn't allow for stationary light waves. Maxwell's equations predicted that electromagnetic waves, including light, must always travel at a specific speed. frozen light, stationary light, light moving at any speed other than light speed, simply wasn't physically possible according to these equations. This paradox nagged at Einstein for years, a decade of wondering, thinking, turning the problem over in his mind. The solution he eventually reached was radical. Maybe the premise was wrong. Maybe it wasn't possible to run alongside a beam of light at all. Maybe light always travels at the same speed relative to any observer, no matter how fast that observer is moving. This became the foundation of special relativity, published in 1905 when Einstein was just 26 years old and working as a patent clerk in Bern, Switzerland. The paper was titled "On the Electrodynamics of Moving Bodies," and it contained one of the most revolutionary ideas in the history of science. Einstein built his theory on two simple postulates. The first postulate, which he called the principle of relativity, states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a viewpoint that isn't accelerating. If you're on a smoothly moving train with the windows covered, no experiment you perform inside the train can tell you whether you're moving or stationary. All motion is relative. There's no absolute state of rest. The second postulate states that light always travels at the same speed in a vacuum, regardless of the motion of the light source or the observer. Whether you're moving toward a light source or away from it, whether the source is moving toward you or away from you, you'll always measure light traveling at exactly the same speed. 186,282 miles per second. These two postulates seem almost reasonable when stated individually. The first one had been around since Galileo. The second one was essentially what the Michelson-Morley experiment had shown. But together they have consequences that violate everything we think we know about how the world works. Consider this situation. You're on a train moving at half the speed of light. That's about 93,000 miles per second. You turn on a flashlight and shine it toward the front of the train. Common sense says that from the perspective of someone standing on the platform, watching the train pass, that light beam should be traveling at 1.5 times the speed of light. The train's speed plus the light's speed. That's how velocities add, right? But Einstein's second postulate says no. The person on the platform will measure that light traveling at exactly the speed of light. Not 1.5 times, just the speed of light. The same speed you measure on the train. How can this possibly be true? How can both you on the train and the observer on the platform measure the same beam of light, traveling at the same speed when you're moving at half the speed of light, relative to each other? The answer is that time and space themselves must be flexible. If the speed of light is absolute and constant for all observers, then time and space must adjust to make this possible. Different observers experience time passing at different rates. Objects in motion shrink in the direction they're traveling. Events that one observer sees as simultaneous may not be simultaneous to another observer. This isn't a flaw in our measuring instruments. It's not something going wrong. Time and space genuinely behave this way. Let's use a thought experiment to understand time dilation. Imagine a simple clock made from two mirrors, with a photon of light bouncing between them. Each time the photon bounces from the bottom mirror to the top mirror and back, the clock ticks once. This is called a light clock. If this clock is sitting still relative to you, you see the photon bouncing straight up and down between the mirrors. The distance it travels is just twice the distance between the mirrors. Now imagine this same clock is on a train moving past you at high speed. From your perspective on the platform, the photon doesn't bounce straight up and down anymore. It travels in a diagonal zigzag pattern because while the photon is traveling from bottom to top, the entire clock has moved sideways. The photon has to travel both upward and sideways to reach the top mirror. Then, it travels downward and sideways to reach the bottom mirror again. Here's the crucial point. The diagonal path is longer than the straight up and down path. The photon has farther to travel between bounces from your perspective on the platform. But light always travels at the same speed. That's Einstein's second postulate. So, if the photon has to travel a longer distance at the same speed, it must take more time. Each tick of the moving clock takes longer than each tick of a stationary clock from your perspective. The moving clock runs slow. This isn't peculiar to this particular clock design. Any physical process that can be used to measure time will show the same effect. Chemical reactions, biological aging, radioactive decay, the vibration of atoms, all of these slow down for moving objects. Time itself is slower, not just clocks. The mathematical formula for time dilation involves something called the Lorentz factor, named after Dutch physicist Hendrik Lorentz. The Lorentz factor depends on how fast something is moving as a fraction of the speed of light. At everyday speeds, the factor is essentially equal to 1, meaning time passes normally. But as speeds approach the speed of light, the factor grows without limit. Let me give you concrete numbers. At 10% of light speed, about 18,600 miles per second, the Lorentz factor is about 1.0. Time runs about 0.5% slower, measurable with atomic clocks but not noticeable in human experience. At 50% of light speed, about 93,000 miles per second, the Lorentz factor is approximately 1.15. Time runs about 15% slower. For every hour that passes for a stationary observer, only about 52 minutes pass for someone moving at this speed. At 90% of light speed, the Lorentz factor jumps to about 2.29. Time passes less than half as fast. 1 year for the moving person equals more than 2 years for someone standing still. At 99% of light speed, the factor is about 7.09. Time is more than 7 times slower. At 99.9%, it's 22.4. Over 20 times slower. As you approach light speed, the Lorentz factor grows without limit. At exactly light speed, it would be infinite, which is why nothing with mass can reach that speed. It would require infinite energy. This sounds like science fiction, but it's been verified countless times in laboratories around the world. The most direct demonstration comes from particles called muons. Muons are created when cosmic rays from space slam into Earth's upper atmosphere, about 9 to 12 miles up. Muons are like heavy electrons and they're unstable. A muon at rest decays into other particles with a half-life of about 2.2 microseconds. That means if you start with 1,000 muons sitting still, after 2.2 microseconds, about 500 will have decayed. Even if a muon traveled at the speed of light, in 2.2 microseconds it could only travel about 2,000 feet. The muons created by cosmic rays form about 9 to 12 miles up. That's 47,000 to 63,000 feet. They should decay long before reaching the ground. Almost none should make it. Yet we detect muons at ground level constantly. About 1 muon passes through your hand every second as you sit here. How is this possible? The muons created in the upper atmosphere are moving at about 98% of the speed of light. At this speed, time dilation is significant. From our reference frame on the ground, the muon's internal clock runs about 5 times slower than ours. The muon's 2.2 microsecond half-life becomes about 11 microseconds from our perspective. That's enough time for the muons to travel from the upper atmosphere to the ground before most of them decay. From the muon's own reference frame, something different is happening. Time passes normally for the muon. It still only lives 2.2 microseconds by its own clock. But because it's moving so fast, the distance from the upper atmosphere to the ground appears contracted. What we measure as 9 miles appears to the muon as less than 2 miles, so it can traverse the distance in its short lifetime. Both explanations describe the same physical reality, from different perspectives. Ground observers see time dilation extending the muon's life. The muon experiences length contraction, making the journey shorter. Scientists have measured this directly. They've placed muon detectors at different altitudes and counted how many muons survive at each height. The numbers match Einstein's predictions precisely. Particle accelerators provide even more dramatic demonstrations. At facilities like CERN in Switzerland, physicists accelerate particles to speeds within a tiny fraction of light speed. The Large Hadron Collider accelerates protons to 99.9991% of light speed. That's 7 nines after the decimal. At this velocity, the Lorentz factor equals about 7,460. Time passes 7,460 times slower for the protons than for us. Many particles created in high-energy collisions decay quickly. Pions, for example, have a rest lifetime of about 26 nanoseconds. Even at light speed, a pion could only travel about 25 feet in 26 nanoseconds. But when pions are accelerated to near light speed in an accelerator, they can travel hundreds of feet or even miles before decaying. Their lifetimes are extended by exactly the Lorentz factor corresponding to their velocity. Now let's apply this to GPS satellites. The satellites orbit at about 8,700 miles per hour, or roughly 14,000 kilometers per hour. This is only about 0.01% of the speed of light. That sounds incredibly slow by relativistic standards, but it's fast enough for time dilation to matter. At this speed, the Lorentz factor is about 1,083. That's a tiny difference from 1, but it's measurable. It means the satellite's clock runs slow by a factor of about 8.3 parts in 10 billion. Over the course of one day, which is 86,400 seconds, this amounts to about 7.2 microseconds. The satellite's clock loses about 7 microseconds per day compared to a clock on the ground, purely due to its velocity. This is special relativity in action. The satellite is moving, so its clock runs slow from our perspective on the ground. 7 microseconds per day doesn't sound like much. But remember, light travels about 300 meters, roughly 1,000 feet in 1 microsecond. So 7 microseconds equals about 2,100 meters, or roughly 1.3 miles. If this were the only effect, GPS positions would drift by more than a mile every day due to special relativity alone. But this isn't the only effect. There's a second influence on the satellite clocks, one that works in the opposite direction. This second effect comes from general relativity, Einstein's more comprehensive theory of gravity, published in 1915. And it turns out that gravity doesn't just pull objects together, it warps time itself. 10 years after publishing Special Relativity, Einstein completed what many consider his greatest achievement. General relativity. If special relativity showed that time and space are flexible, general relativity showed that they're not just flexible, they're curved, bent, warped by the presence of mass and energy. And this curvature isn't just some abstract mathematical concept. It's gravity itself. Gravity isn't a force pulling objects together across empty space. It's the shape of space-time, the geometry of reality. Einstein spent nearly a decade working out the mathematics of general relativity, from 1907 to 1915. It was the hardest intellectual work of his life. He had to learn advanced mathematics he'd never studied before, tensor calculus and differential geometry, to express his ideas. He worked with his mathematician friend Marcel Grossmann to master these tools. He made mistakes, published wrong results, corrected them, and tried again. But the core idea came to him in 1907, in what he later called the happiest thought of his life. Einstein imagined a worker falling off a roof. While the worker is falling, Einstein realized, the worker doesn't feel their own weight. They're weightless. If they dropped a hammer while falling, the hammer would float next to them, falling at the same rate. From the worker's perspective, they're not falling at all. They're floating in empty space. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station. But Einstein realized something profound. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't actually floating in zero gravity. They're falling toward Earth, but they're also moving sideways fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. Einstein realized that being in free fall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet, feeling gravity pull you down. You can't tell the difference. This is called the equivalence principle. Acceleration and gravity are equivalent. They're the same thing. And this was the key insight that led Einstein to general relativity. If acceleration and gravity are the same thing, and if special relativity says that acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space-time. The classic analogy is a rubber sheet. Imagine stretching a flat rubber sheet taut. If you place a heavy ball in the middle, it creates a dip, a depression in the sheet. Now, if you roll a smaller ball across the sheet, it will curve toward the heavy ball. Not because the heavy ball is pulling it, but because the sheet itself is curved. The small ball is trying to roll in a straight line, but the curved sheet forces it to follow a curved path. This is what mass does to space-time. The sun, with its enormous mass, curves space-time around it. Earth is trying to move in a straight line through space, but the curved space-time around the sun forces Earth to follow a curved path. That curved path is Earth's orbit. Now, this rubber sheet analogy has limitations. The rubber sheet is two-dimensional. Real space-time is four-dimensional, 3 dimensions of space plus 1 of time. Also, the analogy shows spatial curvature, but not temporal curvature. In general relativity, time itself is affected by gravity. Time passes more slowly near massive objects. This isn't just clocks running slow, it's actual time, the fundamental flow of causality. 2 identical clocks, one near a massive object and one far away, will tick at different rates. The one near the massive object runs slower. Think about what this means. Gravity doesn't just pull on objects. It changes the rate at which time passes. The stronger the gravitational field, the slower time runs. This is called gravitational time dilation. If you're standing at the base of a mountain, time runs slightly slower for you than for someone standing at the summit. The person at the base is deeper in Earth's gravitational field, so time passes more slowly for them. The effect is tiny, but it's real. The first experimental test of gravitational time dilation was performed in 1959 by Robert Pound and Glenn Rebka at Harvard University. They used a 74-foot tall tower in the Jefferson Physical Laboratory. They placed a gamma-ray source at the bottom and a detector at the top. As a gamma ray climbs up the tower, it's moving away from Earth, working against gravity. This costs energy. The gamma ray loses a tiny bit of energy, which means its frequency decreases. General relativity predicted exactly how much the frequency should decrease. The predicted shift was about 2.5 parts in 10 to the 15th power. Absurdly tiny. But Pound and Rebka built equipment sensitive enough to measure it. The gamma ray's frequency decreased by exactly the predicted amount over just 74 feet. Gravity's effect on time is measurable. Modern optical atomic clocks are so precise they can detect gravitational time dilation over a height difference of just 1 centimeter. In 2010, researchers at NIST built clocks accurate to within 1 second in 3.7 billion years. Raise one of these clocks by 12 inches and it ticks measurably faster because gravity is slightly weaker, 1 foot higher. This opens applications beyond testing physics. You could use ultra-precise clocks as gravitational sensors to map tiny variations in Earth's gravitational field, potentially helping locate underground water or mineral deposits. But for GPS, what matters is the effect on satellite clocks. The satellites orbit at about 12,150 miles above Earth's surface. At this altitude, they're much farther from Earth's center of mass than we are on the ground. The gravitational field they experience is weaker. Specifically, gravity at GPS orbital altitude is only about 56% as strong as gravity at Earth's surface. And because gravity is weaker up there, time runs faster. The calculation requires general relativity. You need to account for the difference in gravitational potential between the satellite's altitude and the ground. When you work through the mathematics, you find that at GPS orbital altitude, clocks gain about 45.9 microseconds per day, compared to clocks on Earth's surface. This is gravitational time dilation. The weaker gravity at altitude makes time run faster. To put this in perspective, imagine 2 identical twins. One stays on Earth, the other goes to live on a GPS satellite for a year. When they reunite, the twin on the satellite would have aged about 16.7 milliseconds more than the twin on Earth. It's a tiny difference, but it's measurable and real. The satellite twin literally experienced more time passing. The key insight is that gravity warps time. The deeper you are in a gravitational well, the slower time passes from the perspective of someone farther out. Think of it like being at the bottom of a valley versus standing on a hilltop. At the bottom, you're deeper in Earth's gravitational field. Time runs slower. On the hilltop, time runs faster. GPS satellites are way up on the hilltop, 12,450 miles above the surface. Time runs significantly faster for them than for us down in the valley. Let's understand why this matters for GPS. Remember, GPS works by measuring the time it takes for radio signals to travel from satellites to your phone. The satellites broadcast timestamps from their atomic clocks. Your phone receives these timestamps and calculates how long the signals took to arrive. But if the satellite's clock is running fast by 45 microseconds per day, those timestamps are wrong. The satellite thinks more time has passed than actually has from your phone's perspective. This throws off the distance calculation. Light travels about 300 meters, roughly 1,000 feet, in 1 microsecond. So 45 microseconds equals about 13,500 meters, or roughly 8.4 miles. If you didn't correct for gravitational time dilation, your GPS position would drift by more than 8 miles every day. Now, here's where it gets interesting. We have 2 effects working in opposite directions. Special relativity says the satellite clocks should run slow by about 7 microseconds per day because they're moving at 8,700 miles per hour. General relativity says the satellite clocks should run fast by about 45 microseconds per day because they're in weaker gravity. What's the net result? The gravitational effect is larger, so the clocks run fast overall. Subtract the 7 microseconds lost from velocity from the 45 microseconds gained from gravity, and you get a net gain of about 38 microseconds per day. This is the combined relativistic effect on GPS satellite clocks. They run 38 microseconds per day faster than clocks on the ground when you account for both special and general relativity. To convert this to distance error, light travels about 300 meters per microsecond, so 38 microseconds equals about 11,400 meters, or roughly 7 miles. Without relativistic corrections, your GPS would drift by 7 miles every single day. After 1 week, it would be off by 49 miles. After 1 month, over 200 miles. The system would be completely useless. You'd look at your phone and see yourself somewhere in a completely different city. The blue dot would be lying to you, drifting farther from your actual position each day. This isn't theoretical, it's real, and it was recognized before GPS was even built. When engineers were designing the system in the 1970s, there was debate about whether these relativistic effects would matter. Some thought they could be ignored initially and corrected later. But physicists insisted the effects were large enough to destroy the system's accuracy from day one. They were absolutely right. The solution engineers implemented is elegant. Before a GPS satellite is launched, while it's still on the ground, technicians set its atomic clocks to run at a slightly different frequency than ground clocks. Instead of oscillating at exactly 10.23 megahertz, the satellite clocks are set to 10.229999943 megahertz. That's a difference of about 4.567 parts in 10 billion. A tiny adjustment, but crucial. Once the satellite reaches orbit and begins experiencing the combined effects of its orbital velocity and the weaker gravitational field, this pre-adjusted frequency causes the clock to tick at exactly the right rate as measured from the ground. The relativistic effects are perfectly cancelled by engineering. The clocks are deliberately built to be wrong on Earth, so they'll be right in orbit. Every GPS satellite currently in operation has this correction built in. Every navigation calculation your phone makes depends on these clocks running at their adjusted frequency. Every time you use GPS, you're relying on both special and general relativity being correct. Einstein's equations aren't just abstract theory. They're practical engineering built into the hardware of satellites orbiting above us right now. Let's take a moment to appreciate what we've just learned. Two completely separate effects from two different theories of relativity are acting on GPS satellite clocks simultaneously. Special relativity, published in 1905, tells us that moving clocks run slow. The GPS satellites are moving at 8 to 700 miles per hour, which causes their clocks to lose about 7 microseconds per day compared to clocks on the ground. General Relativity, published in 1915, tells us that clocks in weaker gravitational fields run fast. The GPS satellites are 12,550 miles above Earth's surface, where gravity is weaker, which causes their clocks to gain about 45 microseconds per day. These two effects work against each other. One makes the clocks run slow. The other makes them run fast. And the net result, when you do the math, is that the satellite clocks run fast by about 38 microseconds per day. This is the number that matters. 38 microseconds. It sounds tiny. It is tiny. But in the world of GPS, where light travels 1 foot in 1 nanosecond, 38 microseconds is enormous. Let's convert this time difference into a distance error so you can really feel what it means. Light travels at 299,792,458 meters per second. That's about 300 meters per microsecond, or roughly 1,000 feet per microsecond. So if the satellite clocks are off by 38 microseconds, the distance calculation is wrong by about 38 times 300 meters. That's 11,400 meters, or about 7 miles. 7 miles of error accumulating every single day. Think about what this means in practical terms. You turn on your phone's GPS in the morning. It shows you at your home address. Everything looks correct. By the end of the day, without relativistic corrections, your phone would think you're 7 miles away from where you actually are. By the end of the week, the error would be 49 miles. By the end of the month, about 210 miles. Within 2 months, the GPS system would think you're in a completely different state from where you actually are. The blue dot on your map would be wandering across the landscape like a ghost, completely disconnected from reality. every car using GPS navigation would be hopelessly lost. Every airplane relying on GPS for precision approaches would be in danger. Every ship using GPS for navigation would be off course. The entire system would be worthless. This isn't a hypothetical problem that might happen. This is what would happen, guaranteed, if we didn't correct for Einstein's relativistic effects. The math is clear. The predictions are precise, and the consequences are catastrophic if you ignore them. So how do engineers solve this problem? How do they make sure the satellite clocks stay synchronized with ground clocks despite the 38 microseconds per day drift? There are actually two solutions, and GPS uses both. The first solution is the elegant one, the one that shows real understanding of the physics. Before a GPS satellite is launched, its atomic clocks are pre-adjusted. They're set to tick at a different frequency than they would on the ground. Remember, the standard frequency for GPS atomic clocks on the ground is 10.23 megahertz. That's 10,230,000 cycles per second. But the satellite clocks aren't set to this frequency. Instead, they're set to 10.229999543 megahertz. That's 10,229,999,9443 cycles per second. The difference is about 0.00457 megahertz, or about 45.7 hertz. Out of more than 10 million cycles per second, the satellite clocks are set to oscillate about 46 times per second slower than ground clocks. That's a difference of about 4.567 parts in 10 billion. Incredibly tiny, but crucial. Here's what happens. On the ground, before launch, these clocks are running slow compared to standard GPS clocks. They're ticking at the wrong rate. If you left them on the ground, they would gradually fall behind. But you don't leave them on the ground, you launch them into orbit. Once the satellite reaches its operational altitude of 12,350 miles and begins moving at its orbital velocity of 8,700 miles per hour, something remarkable happens. The clock experiences time dilation from its velocity, which tries to make it run even slower, losing about 7 microseconds per day. But it also experiences gravitational time dilation from being in weaker gravity, which tries to make it run faster, gaining about 45 microseconds per day. The net effect is that it gains about 38 microseconds per day. But wait. The clock was already pre-slowed on the ground. It was set to run slow by exactly the amount needed to compensate for the relativistic effects it would experience in orbit. So what happens? The pre-slowing cancels out the relativistic speed-up. The clock that was running slow on the ground now runs at exactly the right rate in orbit. From the perspective of observers on the ground, the satellite clock ticks at exactly 10.23 megahertz, the standard GPS frequency. The relativistic effects are perfectly neutralized by the pre-adjustment. Think about what this means. Engineers built a clock that's deliberately wrong on Earth so that it would be right in space. They used Einstein's equations to calculate exactly how wrong it needed to be on the ground, so that once it experienced the warped spacetime of orbital flight, it would tick at precisely the correct rate. This is physics being used not just to understand the universe, but to engineer functional technology. It's relativity theory becoming relativity practice. Every GPS satellite launched since the system became operational in the 1990s has had this correction built in. The clock manufacturers receive specifications telling them exactly what frequency to set. The satellites are tested on the ground with their pre-adjusted clocks running at the wrong rate. Then they're launched, and once they reach orbit, their clocks magically become right. But there's a second correction that happens continuously while the satellites are in orbit. The pre-adjustment handles the average effect, but GPS satellites don't maintain perfectly circular orbits at perfectly constant altitudes. Their orbits are elliptical, though only slightly. As a satellite moves along its elliptical orbit, its altitude changes. When it's at the highest point in its orbit, called apogee, it's farther from Earth and gravity is slightly weaker. When it's at the lowest point, called perigee, it's closer to Earth and gravity is slightly stronger. These altitude changes affect gravitational time dilation. Higher altitude means weaker gravity, which means faster time. Lower altitude means stronger gravity, which means slower time. Also, the satellite's velocity changes slightly as it moves along its elliptical orbit. It moves slightly faster at perigee and slightly slower at apogee. This affects the velocity time dilation, so the net relativistic effect isn't constant. It varies as the satellite moves through its orbit. To handle this, GPS satellites constantly receive updates from ground control stations. There are monitoring stations around the world that track every satellite continuously. These stations measure each satellite's exact position and velocity at all times. They calculate the instantaneous relativistic corrections needed based on where the satellite is in its orbit. Then they upload correction data to the satellites, and the satellites include this information in the signals they broadcast. When your phone receives a signal from a GPS satellite, that signal doesn't just contain a timestamp in the satellite's position. It also contains relativistic correction factors. Your phone applies these corrections when calculating its distance from the satellite. So even though the satellite's clock is running at a slightly variable rate due to orbital variations, the system compensates for it. The combination of the pre-adjusted clock frequency and the real-time corrections uploaded from ground control keeps everything synchronized to within nanoseconds. This is engineering at its finest. It's taking two abstract theoretical predictions from Einstein's relativity, predictions that seemed like pure science when they were first made in 1905 and 1915, and turning them into practical corrections that make a global navigation system work. Without these corrections, GPS would be useless. With them, GPS achieves accuracy of a few meters, good enough to guide you to a specific building on a specific street in a specific city anywhere on Earth. And it's not just GPS. Russia's GLONASS system, Europe's Galileo system, and China's Beidou system all use the exact same relativistic corrections. The numbers are slightly different because the satellites orbit at different altitudes, but the physics is identical. GLONASS satellites orbit at about 90,100 kilometers. Galileo satellites orbit at about 23,200 kilometers. Beidou uses multiple orbits, some at 35,786 kilometers in geostationary orbit. Each system calculated the specific relativistic effects for its particular orbital configuration, and each system pre-adjusts its satellite clocks accordingly. This is a beautiful demonstration of a fundamental truth about physics. The laws of nature don't care about human politics or national boundaries. They work the same way everywhere. Einstein's equations apply equally to American satellites, Russian satellites, European satellites, and Chinese satellites. Every nation that has built a satellite navigation system has had to grapple with the same relativistic effects. And every nation has had to use the same solutions, the same mathematics, the same adjustments. You can't negotiate with the universe. You can't lobby for different laws of physics. You have to accept reality as it is and design your technology accordingly. The fact that GPS works, that you can pull out your phone anywhere on Earth and know your position to within a few meters, is proof that Einstein was right. His theories aren't just abstract ideas, they're accurate descriptions of how the universe actually works. And we've built our civilization's navigation infrastructure on that foundation. There's something profound about the fact that every satellite navigation system on Earth, regardless of which country built it or operates it, uses the exact same relativistic corrections. Think about that for a moment. We live in a world of competing nations, different languages, conflicting ideologies, and geopolitical tensions. Countries argue about borders, trade policies, military alliances, and countless other issues. But when it comes to the fundamental physics that makes GPS work, there's no disagreement. There's no American version of relativity versus a Chinese version or a Russian version. There's just Einstein's relativity, and it works the same way for everyone. The United States built GPS starting in the 1970s, with the system becoming fully operational in 1995. The satellites orbit at 20,200 kilometers and experience a net relativistic time shift of about 38 microseconds per day. Russia built GLONASS, which became operational in the mid-1990s. Their satellites orbit at 90,100 kilometers, slightly lower than GPS, and experience a net relativistic time shift of about 36 microseconds per day. The number is different because the altitude is different, but the physics is identical. The same equations apply. Europe developed Galileo, which achieved initial operational capability in 2016. Galileo satellites orbit at 23,222 kilometers higher than GPS and experience a net relativistic time shift of about 42 microseconds per day. Again, different number, same physics, same equations, same relativistic corrections. China developed Beidou, which became globally operational in 2020. Beidou is particularly interesting because it uses 3 different types of orbits. Some satellites are in medium Earth orbit at about 21,500 kilometers. Some are in inclined geosynchronous orbit at 35,186 kilometers. And some are in geostationary orbit, also at 35,186 kilometers. Each orbital configuration experiences different relativistic effects. The medium Earth orbit satellites have corrections similar to GPS. The geostationary satellites, which orbit much higher and move much faster to complete one orbit per day, experience different combinations of velocity and gravitational time dilation. But all of them use Einstein's equations to calculate the corrections. China didn't develop a different theory of relativity. They use the same theory everyone else uses, because it works. There's no alternative that fits the data. This universality is one of the most beautiful aspects of physics. The laws of nature are the same everywhere. An electron in Beijing behaves exactly like an electron in New York. A photon in Moscow travels at the same speed as a photon in Brussels. Gravity works the same way in China as it does in the United States. The curvature of spacetime follows the same equations, regardless of who's measuring it. This might seem obvious, but it's actually remarkable. These laws weren't decided by international treaty or negotiated at diplomatic summits. They were discovered through observation and experiment, and they turn out to be universal. Every GPS engineer, regardless of which country they work for, has to account for the fact that a clock in orbit runs about 38 microseconds per day faster than a clock on the ground at GPS altitude, or about 36 microseconds per day faster at GLONASS altitude, or about 42 microseconds per day faster at Galileo altitude. The specific number depends on the orbital parameters, but the underlying physics is identical. If you ignore these effects, your navigation system fails. It doesn't matter how good your engineers are or how advanced your technology is. If you don't correct for Einstein's relativistic effects, your system simply doesn't work. This creates an interesting situation. Countries that might disagree on almost everything else have to agree on this. They have to use the same physics, the same mathematics, the same corrections, because the universe doesn't care about politics. It operates according to laws that are indifferent to human concerns. You can't negotiate with space-time curvature. You can't vote on whether time dilation exists. You have to accept reality as it is and work within its constraints. There's something humbling about this. For all our differences, for all the ways we divide ourselves into nations and ideologies and competing interests, we all live in the same universe, governed by the same laws. When a Russian engineer calculates relativistic corrections for GLONASS, and an American engineer calculates corrections for GPS, and a Chinese engineer calculates corrections for Beidou, and a European engineer calculates corrections for Galileo, they're all using Einstein's field equations from 1915 and Einstein's special relativity from 1905. The same equations that have been tested thousands of times over the past century and have never failed. This is what makes science different from other human endeavors. Scientific theories aren't matters of opinion or cultural preference. They're either consistent with observations or they're not. Either your predictions match reality or they don't. And when it comes to GPS, the predictions are spectacularly precise. The relativistic corrections work. They work for American satellites and Russian satellites and European satellites and Chinese satellites. They work because Einstein's theory accurately describes how time and space behave near massive objects and at high velocities. In a very real sense, GPS represents humanity's mastery of space-time geometry. We've learned to measure time precisely enough and understand physics deeply enough that we can navigate our planet using invisible signals from machines orbiting thousands of miles above us. We've turned Einstein's abstract mathematical insights about the nature of reality into a practical tool that billions of people use every day without thinking about it. When you pull out your phone and open a map application, you're accessing a system that spans the globe. Satellites from multiple nations, ground stations on multiple continents, corrections based on physics that took centuries to discover and decades to confirm. All of it working together seamlessly because the underlying physics is universal. This is perhaps the most profound lesson of GPS and relativity. The universe has rules. Those rules don't change based on who's observing them or which country they're in. They're the same everywhere, for everyone, always. And when we understand those rules deeply enough, when we can describe them mathematically and test them experimentally, we can build technologies that would seem like magic to previous generations. We can hold a small device in our hands that communicates with satellites in orbit, accounts for the warping of space-time, and tells us exactly where we are on Earth to within a few meters. That's not just engineering. That's applied Einstein. That's relativity in your pocket. And it works the same way for everyone, everywhere, because physics doesn't recognize borders. The equations are universal, and so is their power to help us navigate our world. We've spent most of this journey exploring the practical side of relativity, how Einstein's equations make GPS work, how time dilation affects satellite clocks, how space-time curvature changes the rate at which time passes. But now, let's dive into something deeper, something more unsettling. What does all of this mean for the nature of time itself? What does it mean that time passes at different rates for different observers? If there's no universal now, if different people can legitimately disagree about what's happening at this moment in distant places, then what is time? Is it even real? Or is it, as Einstein once suggested, a stubbornly persistent illusion? These aren't just philosophical questions. They emerge directly from the mathematics of relativity. And they've troubled physicists and philosophers for over a century. Let's start with something Einstein wrote in 1955, just weeks before his own death. His lifelong friend Michel Besso had died, and Einstein wrote a letter to Besso's family. In it, he said something remarkable. "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." Think about what Einstein is saying here. The distinction between past, present, and future is an illusion. not a mistake in our measurements, not an approximation, an illusion. Einstein believed that past, present, and future all exist equally, that they're all equally real. This view is called the block universe, or sometimes eternalism. It's the idea that all of space-time, all events that have ever happened or will ever happen, exist together in a four-dimensional structure, like a block of ice with all moments frozen in place. In this view, you don't move through time. You exist as a four-dimensional object, stretched through space-time. There's a version of you reading these words right now. There's a version of you 5 minutes ago making the decision to read this. There's a version of you tomorrow morning waking up. All of these versions exist simultaneously in the block universe. What we call the passage of time is just our consciousness moving through the block, experiencing one slice at a time. But all the slices exist. Right now, in the block universe framework, everything that will happen tomorrow already exists. It's just in the future part of the block. Everything that happened yesterday still exists in the past part of the block. Nothing ever really comes into being or ceases to exist. It all just is, stretched across the four dimensions of space-time. This sounds crazy. It violates everything we experience about time. We feel time flowing. We remember the past, but not the future. We can change what happens next, but not what already happened. How can Einstein say this is all an illusion? The argument comes directly from special relativity, and the relativity of simultaneity. Remember, in special relativity, different observers moving at different velocities disagree about which events are simultaneous. What happens now for one observer happens at a different time for another observer moving relative to the first. There's no universal present moment. Now here's the philosophical problem. If we say that only the present moment exists, that the past has ceased to exist, and the future doesn't exist yet, then we have a contradiction, because different observers disagree about what the present moment is. An event that's in your present might be in my future or my past, depending on our relative motion. So, does that event exist or not? If only the present exists, then whether an event exists depends on who's observing it. That seems absurd. Either something exists or it doesn't. It can't exist for you, but not for me. The only way to resolve this contradiction is to accept that all events exist equally. Past, present, and future are all real. What differs is only our perspective on them, which events we happen to be experiencing at any given moment. This is the block universe. It's sometimes called the growing block universe if you want to preserve some sense that the future is different from the past, that it hasn't happened yet. In the growing block view, the past and present exist, but the future is genuinely open, not yet determined. The block grows as time passes, with new moments being added to the past. But this view has its own problems. If the block is growing, when is the edge of the block? What counts as now? And different observers will disagree about where that edge is because of relativity of simultaneity. So the growing block doesn't really solve the problem. Most physicists who think about this carefully end up accepting the full block universe. Past, present, and future all exist. Time doesn't flow. The appearance of flow is something that happens in consciousness, in how we experience the block, but it's not a feature of the block itself. This has disturbing implications. If the future already exists in the block universe, then everything that will happen is already determined. There's no free will, no genuine choice, no ability to change what happens next. You experience yourself making decisions, but in the block universe framework, those decisions are already part of the structure. The version of you tomorrow making a decision exists just as much as the version of you now thinking about making that decision. The decision is already made in the sense that it's already part of the four-dimensional block. You're just experiencing it sequentially as your consciousness moves through time. Many people find this deeply uncomfortable. It seems to rob life of meaning if everything is already determined, already laid out in the block. But here's a counter-argument. Even if the block universe is true, even if all moments exist equally, that doesn't change your experience. You still experience time flowing. You still experience making choices. You still experience uncertainty about the future. The subjective feeling of free will, the experience of deciding and choosing, remains the same whether or not the future is already determined. Some philosophers argue that what matters is the experience, not the underlying metaphysics. Whether or not you could have chosen differently in some absolute sense, you experienced yourself choosing. That's what matters. Others disagree, arguing that genuine free will requires that the future be open, that multiple futures be possible, and that your choices select which one becomes real. There's another aspect of time that relativity doesn't explain: the arrow of time. Why does time seem to flow in one direction? Why do we remember the past, but not the future? Why can we change the future, but not the past? Einstein's equations are time symmetric. They work equally well whether time runs forward or backward. You can run any physical process backward in time according to relativity, and it follows the same laws. A movie of orbiting planets played in reverse still shows the planets obeying Einstein's equations. So why does time have a direction in our experience? The answer seems to come from thermodynamics, from the second law, which states that entropy always increases. Entropy is a measure of disorder, of the number of possible arrangements a system can have. The second law says that closed systems always evolve toward higher entropy, toward more disorder. This gives time its arrow. Think about breaking an egg. You can easily break an egg and scramble it. The ordered structure of the egg, shell, white, and yolk, separated, becomes disordered. Entropy increases. But you never see a scrambled egg spontaneously unscramble itself and reform into a whole egg with intact shell. That would require entropy to decrease, which the second law forbids. So there's an asymmetry. Eggs break easily going forward in time, but never unbreak, going backward. This asymmetry applies to everything. Coffee and cream mixed in a cup don't spontaneously unmix. Shattered glass doesn't reassemble itself. Deceased organisms don't come back to life. All of these processes involve entropy increasing, disorder spreading, and they only happen in one direction. This is why we remember the past, but not the future. Memory is a physical process that involves recording information, creating ordered structures in our brains. Those structures form in the direction of increasing entropy, the direction we call future. We can't remember the future because memory formation is an entropy-increasing process that points towards the future. So we have two aspects of time. The relativity of simultaneity, which suggests the block universe where past, present, and future all exist equally. And the arrow of time from thermodynamics, which gives us a direction, a sense of past versus future, a flow from order to disorder. These two aspects fit together uneasily. The block universe suggests time doesn't really flow. The arrow of time suggests it does flow from low entropy to high entropy. Reconciling these views remains an open question in physics and philosophy. What we can say is that GPS and relativity force us to take these questions seriously. When you hold your phone and see that blue dot showing your position, you're seeing the practical result of understanding that time is not what it seems, that it runs at different rates in different places, that it's intimately connected with space in ways that our ancestors never imagined. Einstein's equations work. They make GPS possible, and they also force us to reconsider our most basic assumptions about the nature of reality, time, and our place in the universe. These are deep waters, and we're still learning to navigate them. But GPS proves we understand something real about how time works, even if we don't fully understand what time is. Let's step back and take in the full picture of what we've explored tonight. We started with something simple, a blue dot on a phone screen. A dot that tells you where you are, that guides you through unfamiliar streets, that helps you find your way home. And we discovered that this simple dot, this everyday tool that billions of people use without a second thought, depends on one of the deepest truths about reality ever discovered. Time is not constant. Space is not fixed. Reality itself bends and warps in ways that would have seemed like magic to every generation of humans before the 20th century. A man sitting at a desk in Switzerland in 1905, working as a patent clerk with no laboratory and no university position, figured out that time runs at different rates depending on how fast you're moving. 10 years later, he figured out that time also runs at different rates depending on how deep you are in a gravitational field. He worked this out with nothing but pencil, paper, and his extraordinary imagination. He couldn't build satellites. He couldn't test his theories with atomic clocks. He just thought deeply about what light is and how it moves, and what that must mean for the nature of space and time. And now, more than a century later, we've built a global navigation system that depends entirely on his insights being correct. Every GPS satellite orbiting above us right now carries atomic clocks that tick at a pre-adjusted frequency. They're deliberately set to run at the wrong rate on the ground so they'll run at the right rate in orbit. They're engineered to account for the fact that time passes 38 microseconds per day faster at orbital altitude than it does on Earth's surface. Without this correction, the system fails. The blue dot drifts. Your position becomes meaningless. This isn't speculation or theory in the abstract sense. This is tested reality. Billions of people use GPS every single day. It works. And it works because Einstein was right about how the universe operates. Think about the journey humanity took to reach this point. For thousands of years, we assumed light traveled instantly. In 1676, old Roma watched Jupiter's moons and proved that light has a speed. In 1887, Michelson and Morley tried to detect Earth's motion through the ether and found nothing, proving that light's speed is constant regardless of motion. In 1905, Einstein explained what this means. Time and space are relative. In 1915, he showed that gravity isn't a force, but the curvature of space-time itself. Each of these discoveries built on what came before. Each one revealed something unexpected about reality, and each one brought us closer to understanding how the universe actually works, as opposed to how we think it works based on our limited, everyday experience. We evolved on the African savanna, moving at walking speeds in a weak gravitational field. Our intuitions about space and time were shaped by that environment, and those intuitions are wrong when you go beyond that environment. At speeds approaching light speed, time behaves differently. At distances far from massive objects, gravity behaves differently. The universe is stranger than our ancestors could have imagined, but it's not incomprehensible. Einstein showed us that reality follows mathematical laws. We can write down equations that describe how space-time curves, how time dilates, how gravity works, and we can test those equations against observations. And when we do, the equations work. They make predictions. and those predictions come true. This is what makes physics so powerful. It's not just describing what we see, it's revealing underlying principles that explain why things are the way they are. GPS is a triumph of human understanding. We've learned to measure time precisely enough that we can detect differences of billionths of a second. We've learned to build clocks so accurate they lose only 1 second in hundreds of millions of years. We've learned to engineer systems that span the globe, with satellites and ground stations and billions of receivers all working together seamlessly. And we've learned to account for the relativistic effects that would otherwise make the whole system useless. This is applied Einstein. This is relativity turned into technology. Every time you navigate using GPS, you're relying on equations that Einstein worked out over a century ago. You're benefiting from humanity's understanding of how space-time works. You're using knowledge that took 400 years to accumulate, from Romer's observations of Jupiter's moons to Einstein's theories of relativity to the engineering of atomic clocks and satellites. All of that knowledge, all of that effort, all of those insights from brilliant people across centuries and continents compressed into a small device in your pocket that shows you a blue dot on a map. There's something beautiful about this. We are, as Carl Sagan said, a way for the cosmos to know itself. We're made of atoms forged in stars that exploded billions of years ago. Stardust that somehow learned to think, to question, to wonder about its place in the universe. And we've gotten good at it. We've figured out that space and time are woven together. We've figured out that gravity is geometry. We've figured out how to measure time with incredible precision and how to use that precision to navigate our world. We've built satellites that orbit overhead, conversations happening in the silence of space, invisible threads of mathematics connecting machines in orbit to devices in our hands. When you look at that blue dot, you're seeing the culmination of centuries of human curiosity and ingenuity. You're seeing Einstein's genius made practical. You're seeing relativity proven with every step you take. The universe is vast and strange and operates according to rules that challenge our intuitions. But we can understand those rules. We can learn how reality works, describe it mathematically, test it experimentally, and use that knowledge to build technologies that improve our lives. GPS is just one example. There will be others. As we continue exploring the universe, as we continue probing the nature of reality at the smallest and largest scales, we'll discover more truths that seem impossible at first. And if history is any guide, some of those impossible truths will eventually become everyday technology that future generations take for granted. For now, though, we have this. A global navigation system that works because a patent clerk in Switzerland figured out that time is relative. That's remarkable. That's worth appreciating. So the next time you pull out your phone and see that blue dot showing your location, remember what's really happening. Remember the satellites racing overhead at thousands of miles per hour. Remember the atomic clocks ticking away, pre-adjusted to account for relativistic effects. Remember Einstein's equations, proven billions of times per day by billions of users around the world. Remember that you're navigating using the curvature of space-time itself. You're stardust using Einstein's geometry to find your way home. Sleep well tonight, knowing that the universe, for all its strangeness, is knowable. That reality, for all its complexity, follows rules we can discover and understand. This is Space Doze. Signing off. Good night